So on the syllabus, it says today that we are going to talk about a review of complex numbers and then a review of sinusoids. And I'm going to flip the script on that. We're going to talk about sinusoids first, and then we're going to talk about complex numbers. So because I'm changing things up slightly, it is going to impact your homeworks a little bit. So let me explain what I mean by that specifically. Homework set number 18 is all about complex numbers. We are going to cover that material today. Homework set number 19 is all about sinusoids and some trig identities and all that kind of jazz. We are actually going to be covering that today as well. So you should actually, in reality, be ready to handle homework set 19 after the end of today's lecture. That being said, what I'm going to do with Friday's lecture is help to try to bridge the gap of understanding between sinusoids or sinusoidal representation of signals and complex number representation of signals, such that when you actually attempt homework 19, you should be able to use complex number relationship to make the math significantly less terrifying than if you were basing everything off of strictly trig identities. So that's the reason why I'm teaching it in a potentially odd order. Okay. So now that that preface is out of the way, let's talk about some things. So let's first talk about the reason we're looking at sinusoidal signals at all. So we are about to enter a portion of this class that is pretty much entirely devoted to the concept of steady state sinusoidal circuit analysis. And so what that means is we're going to be dealing with circuits where instead of having a DC voltage source, we will have a sinusoidal voltage source or current source. Specifically meaning that that sinusoid has existed for all time. So we are not turning on a sinusoidal source. It has always been sinusoidal, such that our circuit is at a steady state sinusoidal condition, okay? So I'm making that clarification to say that we are not going to worry about the transient analysis of sinusoidal systems. And in fact, the electrical engineers don't actually see that until you get to circuits 3, because the math required isn't necessarily hard, but it's significantly less painful if you have background understanding of the Laplace transform. So we push that off until you're effectively guaranteed to understand how the Laplace transform operates and all that kind of stuff. Okay. All right. So since all of the excitation signals that we are going to be dealing with for the remainder of the class are sinusoidal in nature, we need to have a very good grasp on what a sinusoid is, what its constituent parts are, and how it behaves. Okay. So to that end, I'm going to draw, as per usual, a completely terrible picture because I am not particularly artistic. So just for the sake of argument, let's say that the sinusoidal signal here represents a voltage waveform. As some function of time. Let me put my signal in blue. And like I said, I am quite bad at drawing these, so I'm going to pre-apologize, but we'll get through things. So this blue waveform represents our sinusoidal signal, V of t, and I could express V of t in one of two ways, okay? The first way that I can express it is in terms of a cosine function. So I'm going to have V sub m cosine omega t plus some phase angle theta. And the second way that I could represent this signal would be V of t Vm sine omega t plus some different phase angle phi. We'll talk about what the relationship between theta and phi is and all of that kind of good stuff here in the next several minutes, okay? So let's first start by identifying the common parts of both of these representations, okay? So the first thing that these two representations have in common are their amplitudes, okay? So Vm of t, I don't know why that wrote and didn't scroll my screen. Hold on, my touch screen isn't doing what I want it to do. It's still writing when I touch it. Okay, I'll make this work. So V sub m is the amplitude of the sinusoidal signal. Okay. So what I mean by that explicitly is it's the distance between our horizontal axis and the peak value of our signal. It is also the distance between the horizontal axis and the negative peak value of our signal as well, right? So this represents effectively the size of the sinusoid. So if I have a sinusoidal signal that I'm describing as 5 cosine 120 pi t volts, that means its peak value is +5 and its most negative value is -5, right? So this is the peak value of the signal that is multiplied by this cosine function, which oscillates between +1 and -1, okay? So Vm is simply our amplitude. Cosine and sine, it literally means the exact same thing, okay? So that's our first piece of information, or first part of a sinusoid that we need to understand. Okay? The next thing that we are going to look at is omega. So omega is the angular frequency of the sinusoidal signal. It is always expressed in units of radians per second. And it represents how quickly our signal oscillates in time, okay? So this is a potentially difficult concept. So we are going to tie it back to some things that you're probably familiar with already, okay? So capital T is the period of the sinusoidal signal. And what that means is that it is the total amount of time it takes for one cycle to elapse, right? F is the linear frequency of the sinusoidal signal, and it represents the number of cycles per second. So linear frequency is measured in hertz, where a hertz is just 1/a second. And our period t is typically measured in seconds because it's the amount of time that has elapsed. Okay? So let's talk about the relationship between these two quantities. Okay? So capital T is the time necessary for one cycle to elapse. Our frequency in hertz is the number of cycles that elapses in 1 second. So T and F are just the inverses of each other, right? Because the number of cycles per second, the inverse of that is the number of seconds per cycle, right? So cycles per second is T, or excuse me, F. Seconds per cycle is capital T. So I'll put, I don't know why this isn't just allowing me to touch it and scroll. That's too aggressive. So we can say that T is equal to 1/f. So now let's go back around to omega, okay? So F is our linear frequency, the number of cycles we see per second. Omega is our angular frequency, which tells us the amount that the angle changes per second. Every cycle represents a change in angle of 2 pi. And so from that, we can say that omega is simply 2 pi times F, or 2 pi divided by the period. So trying to tie things back to something that we can explicitly determine by looking at the graph, we now have an understanding of what omega in our mathematical expression represents. Inversely proportional to the period, and then there's also that factor of 2 pi because our angle changes by exactly 2 pi radians as we complete one cycle of the sinusoid. So let me scroll back up here so that we can kind of look at all of this in context, right? Our magnitude is something that we can explicitly measure by looking at our graph because it's just the peak value of our sinusoid. We can now determine omega simply by looking at our graph because we understand how it relates to the period of the sinusoid, which is something that we can determine by looking at things, right? So now we get into this phase angle thing. Okay. So let me ask you guys a question. If I just had cosine of omega t with a phase angle of 0, at what value of time would we expect that sinusoidal signal to hit its maximum value? T is equal to 0 because cosine of 0 is equal to 1, right? So the fact that the signal that I've drawn up here hits its peak value at a time that is different than 0, means that there is some phase angle that is causing this sinusoidal signal to be shifted in time, either to the left, which would mean it would be advanced, so its peak value occurs earlier than we expect it to, or it could be delayed, meaning its peak value occurs later than we would expect it to. For this particular signal, looking at it from the perspective of it being a cosine function, this one is delayed because its peak value occurs at a value of time lowercase t that is greater than 0. Okay. And we can figure out from that time displacement what the phase angle actually is, because it's going to be related to omega as well as that time, right? So let me scroll down here. So theta, and I'll put over here, and phi are the phase angle of the sinusoidal signal. And they represent the amount by which the signal is shifted in time. So let's talk about that a little bit. If theta or phi is negative, our signal is shifted to the left, which we commonly call advanced. By an amount. Call this delta t is going to be equal to our phase angle. Actually, let's use theta, right? So that is an angle measured in radians for now. Let's say that. And then I'm going to divide that by omega so that I have radians per second, which gives us seconds in the numerator. So this is an amount of time shift. So this is how much we're shifted in time to the left. If theta or phi is positive, our signal is shifted to the right, also known as delayed, by an amount delta t is equal to our phase angle divided by omega. So let me scroll back up here so we can look at this graph. And just for the sake of argument, I'm actually going to extend things a little bit here. Like so. Just to illustrate something here. So if we are looking at this particular sinusoidal signal from the perspective of it being a shifted cosine function, would our phase angle theta be a positive quantity or a negative quantity? A positive quantity indicates a time shift to the left. Our peak value is occurring to the right of t is equal to 0. So I argue this is a delayed signal from the perspective of a cosine function. So in reality, our phase angle would be a negative value of theta. If we were looking at this particular signal as a sine function, this would be an advanced signal because it hits 0 at a negative value of t, meaning that it has been shifted to the left, and that would correspond to a positive phase angle phi. I'm focusing on this because it can be very simple to make a mistake. It seems almost counterintuitive, but it's all dealing with the fact that we, on our graph, represent time as negative values of time, meaning the past, or excuse me, negative values of time, meaning the past occur on the left, positive values of time, meaning the future, are on the right. Yes, Walter. T is time. So our angle of 360 degrees, we are going to sweep that entire 360 degrees every period, right? So so that might not be something that's obvious, but our phase angle is a constant. Okay. Right, so since it represents the amount of time that this thing is shifted, the amount of shift does not change. It's the amplitude that's changing over time, because the cosine of the entire argument, omega t plus either theta or phi, is oscillating between 1 and -1, and then back to 1, and so forth, right? So the amplitude is a constant value, Bm is a constant value, but what we see changes in time as t changes. Did I explain that okay? No. The theta or the phi is constant. Omega times t is going from 0 to 360 because omega is radians per second times time gives us an angle measured in radians. So the omega t part is the thing that's actually cycling from 0 to 2 pi over and over and over again. The phase angle phi or the phase angle theta is a constant value that is added to that angle omega t. Did that clear that up? For example, it's 0 at that side. What if you chose the other side? So if I chose this thing right here, this point right here, for instance, that would be indicative of a negative sine function because it is 0 and decreasing at that point in time, right? So what do we know about a sine function? if we just have sine of x, right? So when x is 0, the value of the sine function is 0. When x is a little bit greater than 0, so a positive number, our sine function is increasing. When x is negative, or a little bit less than 0, our sine function is decreasing. So I chose this point in particular to be where my positive sine function would start, because I know that a sine function should be 0 and increasing as it crosses the horizontal axis. Similarly, I chose this point in time to be where my cosine function effectively starts, because I know that cosine of 0 should be 1, and I should see that my function starts decreasing immediately as the cycle starts. So if I chose this point right here, that would be corresponding to the beginning of a negative sine function starting its cycle. So that would be like negative sine shifted to the right. So negative sine with some negative phase angle. If I chose this point right here, this would be negative cosine with some negative phase angle. This point over here would be negative cosine with some positive phase angle, etc. So I have to have a background understanding of how a sine function and a cosine function regularly behaves in order to do this. Yes, Isaiah. That is correct. If the phase angle is negative, the signal is time shifted to the right. Yes, hold on. Yep, and that's, like I said, this is well, now I have myself confused. Okay, hold on. Nope. I just got this part backwards. Yeah. So if our phase angle is negative, we have a right shift. If our phase angle is positive, we have a left shift. This should be delayed. This should be advanced. It would have been easier to just change negative and positive now that I'm looking at this. I apologize for the confusion though. All right, so let's run through this again. That's how easy it is to make a mistake with this. Even your jackass teacher is doing it, okay? So we look at time across this horizontal axis, where negative values of time are the past. Positive values of time are the future, okay? So this is a plot of things as they're occurring, and t is equal to 0 is effectively, let's call it the present, okay? So if our cycle starts in the past, our signal has been advanced, right? Because it's starting earlier than we expected it to. And that means that we have a positive phase angle. If our cycle is starting to the right, our signal has been delayed in time, and we have a negative phase angle. Okay. Are we all on the same page now? I apologize for the confusion. Okay, so what I want to do now is introduce some trig identities. So we have the basics down here. I'm going to scroll to this page. And I want to clarify something here. I'm realistically only expecting you guys to remember like 2 of these things. Yeah, I'm about to hit you with like 10, and we're going to use all 10 of them over the next couple of days. But for your exams, et cetera, I'm only expecting you to remember literally 2 of them. Okay. All right. So our first trig identity that we need to remember is that the sine of let's say omega t is equal to the cosine of omega t minus 90 degrees. So if we want to convert from sine to cosine, we simply subtract 90 degrees from our phase angle. Our second identity is that cosine of omega t is equal to sine of omega t plus 90 degrees. Son of a bitch, now I'm scared I have this backwards. No, this is right. Okay. Negative sine omega t is equal to sine omega t plus or minus 180 degrees. And negative cosine omega t is equal to cosine omega t plus or minus 180 degrees. Yes. So you bring up a very interesting point, Christina. Omega, the angular frequency of a sinusoidal signal, is traditionally expressed, or actually, I say traditionally, always expressed as in units of radians per second. Okay. The phase angles, though, are traditionally expressed in degrees. So if you were ever to try to evaluate something like this in your calculator, that presents a little bit of an issue, in as much as one of those angles has to be changed to the other thing, right? Because if you have an angle expressed in radians plus an angle expressed in degrees, your calculator can only be in one of those settings at a time. So just as a heads up, the conversion factor to go back and forth between those two things is that 180 degrees is equal to pi radians. Meaning that if you want to convert your angle in radians to degrees, you multiply it by 180 over pi. If you want to convert your angle in degrees into radians, you multiply it by pi over 180. And sure, this is what I'm used to, so that's why I did it that way. All right. So these first four trig identities are fairly straightforward. They're just showing you what the relationship is between the sine function and the cosine function. They're just shifted versions of each other. Negative sine means that we're flipping it over the horizontal axis, which just indicates a positive or negative 180 degree phase shift. And it literally does not matter which you use because it's just half a cycle. Same thing for the cosine function. You're just shifting it by half a cycle so that it starts negative effectively, okay? So the plus or minus there is completely and utterly arbitrary. It does not matter which one you use. They are both correct because they both represent exactly 1/2 of a cycle's worth of shift. Is that what you're raising your hand about? Yeah, okay. So these are the basics. The two that I legitimately expect you to remember is how to convert a sine function into a cosine function. So that is simply subtracting 90 degrees from our phase angle. And then how to make a negative cosine function a positive cosine function. And we'll talk about why we need specifically to know those two here in a couple minutes. But before we do that, now we're going to go through several other trig identities. So let's say that I have sine of, let's call this phi1 plus phi2. So sine of an angle plus another angle. Okay. That is equal to sine of my first angle cosine of my second angle plus cosine of my first angle sine of my second angle. If I have cosine of some angle 1 plus some angle 2, that looks like cosine of my first angle, cosine of my second angle, minus sine of my first angle, sine of my second angle. That minus sign in the middle there is absolutely correct. If I have sine of angle 1 minus angle 2, that's going to be sine angle 1 cosine angle 2 minus cosine angle 1 sine angle 2. And then lastly, cosine angle 1 minus cosine angle 2 is cosine angle 1 cosine angle 2 minus, plus sine angle 1 sine angle 2. For the most part, we are only going to use these trig identities on Friday when we analyze a simple circuit in the time domain and see that it is ridiculously difficult. Okay. So I'm just introducing these purely so that when I use them on Friday, you will understand where they came from and you will never be expected to use them again. Just to be really, really clear about that. All right. Another couple of useful trig identities that you were going to see in this class. Cosine of angle 1 times cosine of angle 2. And I've actually showed you this showed this particular trig identity to you guys before, is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. Technically, we could derive this for cosine times sine, sine times cosine, sine times sine, but there's no point because we can express any sine function as a cosine function and just use this thing. So I'm not going to derive it 4 different ways when we can just substitute one of our other relationships in and get the job done. Another one that I'm going to use exactly once is cosine squared of an angle plus sine squared of an angle, and it should be the same angle, so that should be a theta. It's just equal to 1. And then one that you may or may not, and honestly probably did not actually learn in your pre-calculus class, is a foundational trig identity for electrical engineering, and it is what's called Euler's identity. Euler's identity says that the cosine of some angle plus j times the sine of some angle is equal to e to the j at angle. And in about 10 minutes tops, we'll start talking about what J is. So we'll put a pin in that for later.
Yeah, I think there's a derivation of this that we used in DigiQ that's used to find the differential equation with complexes.
Yeah, for sure.
So that's found.
Yep.
No, right now, I mean, is that very correct? Is that J raised to the power of theta?
So E is raised to the power of J theta. J times theta. Yes. So that is E raised to the power of J times theta, just to be clear there. All right. So before we move on from our sinusoidal review, can I go to a new page here? All right. I want to talk about comparing sinusoidal signals. So there are 3 rules that we need to follow when we compare sinusoidal signals, which is part of what we're going to be doing in this class. Okay. The first rule is that all signals must be expressed exclusively as sine functions or cosine functions, which means we need to be able to correctly apply the trig identities number 1 or number 2 in order to make everything in terms of a sine function or everything in terms of a cosine function. Electrical engineering uses a cosine function as its basis, which is why I explicitly only asked you to remember that first trig identity: convert any sine function into a cosine function by subtracting 90 degrees. Okay. So if we had, let's leave this in red, some voltage signal, let's call it VA of t, was 10 cosine 8t plus 40 degrees volts. And we had a second voltage signal, VB of t, that was 14 sine 8t plus 60 degrees volts. If we wanted to compare these two, we would need to convert either the sine function into a cosine function or the cosine function into a sine function. Because I am an electrical engineer, I'm going to choose to convert VB of t from a sine function into a cosine function. And so that would literally just be 14 cosine 8t minus 30 degrees volts. Okay. So I subtract 90 degrees from my phase angle to get my sine function into a cosine functional form. My next rule is that all signals must be expressed with positive amplitudes. So if I had a third function that was VC of t is equal to -7 cosine 8t minus 110 degrees volts. I could express this as cosine of 8t plus 70 degrees volts by shifting this signal exactly 180 degrees. I chose to add 180 degrees because generally speaking, I prefer that my phase angle is somewhere between -180 and +180. There would be nothing remotely wrong with this whatsoever if I chose to express this as 7 cosine 8t minus 290 degrees. Nothing wrong at all because positive 70 degrees and a negative 290 degrees are literally the same angle. So I can choose plus or minus cosine 180 degrees indiscriminately. It will always be correct. My personal preference is to make sure that my angle is effectively in between -180 and +180. So a magnitude never greater than 180 degrees. All right. The third rule, did not realize how much I rely on using my finger to scroll my screen until today when it's not working right. So my third rule here is that all signals must have the same frequency. This can be linear frequency or angular frequency. Since they're related to each other by a constant value, it does not matter which, but they all have to have the exact same frequency. There is no trig identity to fix this. If your signals are oscillating at different frequencies, they cannot be compared to each other for the intents and purposes of this class. All right, so now let's talk about the most common way that we are going to compare sinusoidal signals, and that is the concept of leading and lagging. And once again, we have something that is straightforward, yet also confusing at the same time, okay? So I am going to attempt to very shittily draw these three signals that I have given you guys, VA, VB, and VC. And again, please bear with me in my complete and utter inability. Actually, I'm not going to draw anything. Let's use Desmos. Well, yep. Yes. Yes. So we are, our sinusoidal signals will always be cosines or sine. I'm not saying we will never use the tangent operation. Explicitly, we will use the arctangent operation later today. Yes. Yep, we'll deal with that in a moment. All right. So let's go back to my notes here so I can see what I had. So VA was in red and it was 10 cosine 8t plus 40 degrees. So 10 times cosine of 8x plus 40 degrees. I'm going to multiply this 40 degrees by I over 180 so that my total angle is measured in radians, right? Because 8 radians per second times x, which is measured in radians, gives me something in seconds, excuse me, or an angle in radians, and then 40 degrees times pi over 180 degrees is also an angle in radians. So this is VA and it is in red, and this is a bit busy for my taste. So let's change this x-axis from -2 to +2 so that there's not quite as much stuff going on the screen at the same time. And let's also change our y-axis to go from, let's say, -15 to +15, and then get rid of that stuff. All right, so this signal in red is my VA. VB was 14 cosine 8t minus 30 degrees. So 14 cosine 8x minus 30. Oops, I don't want a subscript. Times pi over 180. That was in blue. And then now I need my signal in green, 7 cosine 8t plus 70 degrees. And it looks like my choice of colors literally coincidentally is the exact same thing as the defaults for Desmos. So that works out pretty great. I don't have to change the colors for anything. All right. So these are my 3 signals, okay? All expressed on the same picture. Let me see if I can make this a little bit larger so that we can have a good understanding of exactly what is going on. All right. So our vertical axis here represents time t is equal to 0, okay? So we can see that our red signal, VA of t, is advanced, right? It's a cosine function. Its value is occurring at t that is less than 0, so it has been advanced by some amount. Our green signal has also been advanced by some amount, and our blue signal has been delayed by some amount, okay? So we would say that our green signal, VC of t, leads our other 2 signals because it hits its peak value in time earlier than the other 2 signals do. We could say that our red signal leads our blue signal, but lags our green signal because it occurs, its peak value occurs earlier in time than that of the blue signal, but later in time than that of the green signal, okay? So that's all that leading and lagging really means. Whichever one hits its peak value in time first is leading everything else. Whatever hits its peak value in time last is lagging everything else. Now, I personally hate looking at signals in the time domain to make this comparison for a couple of reasons. A, it is a little counterintuitive, which we talked about previously, all because of how we interpret time on this linear scale. And B, this is just really busy and I find it visually confusing. Okay. So while we can do it this way, this isn't the way that it is typically preferred to be done by electrical engineers. But when I ask you guys to do this, during a lab, I believe sometime next week, this is what the output of the oscilloscope is effectively going to look like. So you need to be able to interpret this thing as well. All right. So this is looking at leading and lagging in the time domain. Just to clarify again, whichever signal hits its peak value in time earliest is leading the subsequent signals. Whatever signal hits its peak value in time last is lagging the other signals. Yes. Right. So it's lagging because it's delayed, right? So the fact that it hits 0 at t is equal to 0.0654 seconds means that it is delayed in time, right? So our phase angle is a negative quantity here, indicating a delay. So it isn't leading the others, it's lagging because it hits. So actually, let me clarify this a little bit further, because this might be the argument that you're trying to make. If we compare this peak to this peak over here, the blue signal is leading. But realistically, we want to compare the peaks that are closer together, because we could always make the argument, oh, well, this blue signal right here is lagging this green signal by some amount of degrees. It's actually leading this green signal over here by 360 minus whatever this difference was. So it is literally the same thing. And we'll talk about that in a moment when we look at our phase representation of these, which is a lot easier, in my opinion, to interpret what's going on. And that also helps us explicitly quantify things much easier as well. Okay. So now that I have mentioned the topic of a phase diagram, let's put it into practice. Okay. Scrolling too far, there we go. Okay. So a phase diagram is nothing more than a snapshot of these sinusoidal signals at a specific time. And I'm going to choose time t is equal to 0, because that makes everything really easy. I know exactly what my angle is going to be at t is equal to 0. It's just my phase angle, right? So I'm going to draw a graph here. The positive horizontal axis corresponds to 0 degrees. Positive vertical axis is 90. The negative horizontal is plus or minus 180. Scroll correctly, machine. There we go. Nope, too far. And then the negative vertical axis is negative 90 degrees. So my signal in red was 10 cosine 8t plus 40 degrees. So I'm going to represent that on my phase diagram by going out 8 units and then rotating up to 40 degrees. So that would be something like this, right? So this is VA is equal to 8 cosine, actually, I think it was 10 cosine 8t. $40 degrees. So this angle right here why is there such input lag? Is 40 degrees. Oh, hold on, my battery is about to die. Now it isn't. Somebody keeps turning this thing off. Okay. Yeah. So here's VA on our phase diagram. Again, we just took a snapshot of this thing at exactly t is equal to 0. So we have a length of 10 units long with a phase angle of 40 degrees. VB was 14 and a phase angle of minus 30 degrees. So that would be something akin to this. VC was 7 with a phase angle of positive 70 degrees, if memory serves me correctly. Let me look just to make sure. Yep. So when we look at a phase diagram like this, signals that are counterclockwise of our signal of interest are leading, and signals that are clockwise from our signal of interest are lagging. So let me explicitly write something down here so we can see what this means, all right? So I want to find by how much, that much looks written terribly, does VA of t lead VB of t? So what I would do is I would start measuring from VB of t. And because I'm looking for leading, I need to go in the counterclockwise direction until I hit VA of t. So this looks like 30 degrees plus 40 degrees. If I wanted to know, so clockwise, or excuse me, counterclockwise is for leading. If I wanted to know by how much does VC of t lag VB of t, I would need to measure in the counterclockwise, or excuse me, the clockwise direction, because it did counterclockwise a moment ago. So I would go from here all the way around to here. So this guy right here in the center, that looks like 90 minus 30, so that's 60 degrees. Then I have 90 degrees, another 90 degrees. 90 minus 70 degrees is 20. So 180 plus 80 is 260 degrees. Where measuring clockwise is for lagging. So you're going to be asked to do this in your homeworks, in the labs effectively, on exams and all of that kind of good stuff. So I just want to be very, very explicit about the rules. If you're asked by how much does some signal lead VB, you start measuring at VB. If you're asked for leading, you go counterclockwise. If you're asked for lagging, you go clockwise. So the second signal is your reference point that tells you where to start your measurement from. And then leading or lagging tells you in which direction to measure the angle. Okay? That's as hard as it needs to be. I will give you guys one caveat, and this has specifically to do with web work. Web work is an idiot. Okay. This process is 100% correct, but WebWork may tell you that your answer is incorrect. Let me explain why. WebWork does not fundamentally know that 0 and 360 and negative 360 represent the same angle. So whoever programmed the problem might have done this process slightly differently and gotten an equivalent angle, but that's not necessarily the angle that you're going to come up with. So if you're sure of your process, simply add 360 degrees or subtract 360 degrees, and I guarantee you WebWork will tell you that one of those is right. You're not doing anything wrong, it's just coded poorly, and I have not had the time to figure out how to fix that. All right, so I have talked for an hour and 10 minutes about sinusoidal stuff. Now let's talk about complex numbers. Okay, so the first thing that I want to address is the concept of J. J is simply the square root of -1, which most of you guys learned in your math classes was I. But electrical engineers can't use I to represent the square root of -1 because I is current. So we, being as creative as we are, said, hey, let's use J. That's it. Just literally the next letter, okay? So J is just the square root of -1, okay? So let's talk about a couple of things here really quickly while we have J on our minds, okay? I'm going to make a table here. So this is going to be J to the first power, and we know that this is simply the square root of 1. J to the second power is just the square root of -1 squared, which is -1. J to the third power is J squared times J to the first power. So that's just -J. J to the fourth is just J squared times J squared. So that's +1. J to the fifth is just J to the fourth times J to the 1. So that's just J. And it's just going to cycle over and over and over again as we go increasing number of powers, right? What should J to the 0 be? 1, because any number raised to the 0th power is 1. J to the -1 is 1 over J. If we multiplied this by J over J, we would have J divided by J squared. J squared is -1, so J to the -1 is just -J. J to the -2 is just 1 over J squared. So that's -1. J to the -3 is 1 over J squared times 1 over J. So that is -1 times -J is +J, and so on and so forth. So again, it's literally just cycling over and over and over again. I bring this up because some of your calculators cannot handle J to a power greater than 3 or more negative than -3. Okay? So for some of your calculators, if you put in j to the fifth, it will tell you that there's a math error. All you need to do is understand that j to the fifth is the exact same thing as j to the one, and then your calculator can go. So just subtract 4 until you get into the range that your calculator can use, or if it's negatives, add 4 until you get into the range that your calculator can use, because this just cycles over and over and over again. So here are all the different representations of j and all that kind of stuff. Like we can expand this forever, and it's literally just going to go j negative 1, negative j positive 1 over and over and over and over again. Okay. All right, so now that we have a grasp of j, let's talk about an actual complex number. So a complex number is simply a number that contains both a real and an imaginary part, okay? So we can express this in a multitude of ways, the first of which is a rectangular form. And then over here to the right, I'm also going to do a exponential form first. And then over here further to the right is the polar form. And I'm grouping the exponential form and the polar form together because they literally contain the exact same information. It's just shown slightly differently. The polar form is literally just a shorthand notation for the exponential form. Here in the middle of my screen, I'm going to draw a complex plane. Where the horizontal axis is my real axis and the vertical axis is my imaginary axis. So you can think of a complex number as a two-dimensional vector. So let's say that I go out a units in the real direction and b units in the positive imaginary direction to form some complex number that I'm going to call uppercase A, and I'm going to put a bar over it. And that bar is letting me know that I'm dealing with a complex number because I can't write in boldface. So in a textbook, you would typically see a complex number represented by a bold-faced quantity. I choose to put a horizontal bar over it. This complex number A is represented in rectangular form as A plus JB, where lowercase a is the real part of complex number A, and lowercase b is the imaginary part of complex number A. So in rectangular form, this is nothing more than a 2D vector like you would have seen in your math and physics classes, right? I'm going out A units in the real direction and out B units in the imaginary direction, and then adding those two vectors together to make my complex number, okay? Now, let's talk about our exponential form. Okay? So we can see that this complex number has some length. And I'm going to call that length the magnitude of A. Actually, I should have done that in purple. Let me, just for the consistency of colors. And this complex number forms some angle with the positive real axis as the reference point. Okay. So in exponential form, our complex number would be written as the magnitude e to the j theta a. In polar form, this is simply the magnitude angle theta a. So the exponential form and the polar form are literally the exact same thing, just expressed in a slightly different form. Polar form is just shorthand notation so that we don't have to write e to the j all the damn time. Okay. Now, your calculator can interpret rectangular form complex numbers and polar form complex numbers. It cannot handle exponential form complex numbers. Meaning, if I ask you in any way, shape, or form to mathematically manipulate an exponential form complex number, the easiest way would simply be to write it as a polar form complex number in your calculator and then do the math there. You could make it harder but still correct by converting that exponential form complex number into a rectangular form complex number. But I'm going to say this again because at least 5 of you are still going to do it. Your calculator cannot handle an exponential form complex number, period. If you try to put one in, it will give you a math error. Freak out, won't do anything. Polar form complex numbers, it can handle all day. Rectangular form complex numbers, it can handle all day as well. All right. So we now have our 3 basic forms of complex numbers identified and what they represent. Let's talk about how we can go back and forth between them. So let's first start by figuring out how we can convert our rectangular form complex number into our exponential form complex number, right? Or polar form. So using the good old Pythagorean theorem, I can say that the magnitude of A is simply the square root of lowercase a squared plus lowercase b squared, or more generally, this is the square root of the real part of complex number A squared plus the imaginary part of complex number A squared. And I take the square root of the whole thing. And that is literally just Pythagorean theorem. A squared plus b squared equals c squared, where c squared is the square of the magnitude of this complex number, the hypotenuse of our little right triangle here. Our angle, theta A, is nothing more than the arctangent of B over A, or more formally, the arctangent of the imaginary part of complex number A divided by the real part of complex number A. So we now know how to convert from a rectangular representation of our complex number into a polar form or exponential form representation of our complex number. What if we wanted to go the other way around? Well, lowercase a is simply the magnitude of A times the cosine of theta A. Or more formally, the real part of A is the magnitude times the cosine of the angle. Lowercase b is the magnitude of A sine of theta A. Or more formally, the imaginary part of complex number A is the magnitude times sine theta A. So putting this together, what we have is complex number A is the magnitude of A cosine theta A plus J times the magnitude of A sine theta A. And oops, we accidentally came up with Euler's identity. So Euler's identity is the bridge that ties our sinusoidal signals to our complex number representations. All right. So before we move on from this point, where we're just feeling things out and figuring out how to switch back and forth between the two representations, do we have any questions? All right. So I am going to now work an example, and because it's me, I'm going to work an example that breaks this. And then we're going to talk about how to overcome. So let's say that I have a complex number x that is equal to -8 plus j 15. And I want to convert this complex number into a polar form. The magnitude of x is just going to be the square root of 8 squared plus 15 squared. I can't do that in my head. That comes out to be 17. I had no idea that was going to be a nice number. Yep. Our angle, theta x, is going to be the inverse tangent of 15 over -8. And I get -61.927 degrees. Okay. Putting these together, my complex number x must then be 17 angle -61.927 degrees. Who can tell me why that's wrong? So effectively, you're talking about it correctly, articulating it not as ideally as I would prefer. Yeah. So, Parson. So, according to our rectangular coordinates, we have a negative real part and a positive imaginary part, which means this should be in quadrant 2. According to our polar form, we have a negative phase angle, which means that we would be in quadrant 4, right? So what the problem here is specifically is that our calculators literally cannot tell the difference between the arctangent of positive 15 over negative 8 and the arctangent of negative 15 over positive 8. The arctangent operation will always return an angle that is in either quadrant 1, so between 0 and positive 90 degrees, or quadrant 4, meaning between 0 and negative 90 degrees. Since our complex number lies in quadrant 2, we actually need to add plus or minus 180 degrees to this in order to make it correct if we do it by hand. So here's a thought. Let's never do it by hand. Okay. Our calculators can do this conversion for us and get it right 100% of the time. So instead of suffering through things and having to think about what quadrant our number lies in, let's get familiar with how to use our calculators correctly to do this math. So I'm going to start with the TI, folks, because this will be slightly easier for you guys, and I'm concerned I might run out of time, but it'll be okay. So for you TI folks, if we wanted to input the number -8 plus J15, I would type -8 plus 15, and then I would press the pi button 3 times. Okay, so pressing the pi button 3 times gives me the imaginary operator I, which we know is the same thing as J. To convert this number into its polar form, I press second and then the pi button to get my complex menu. If I scroll down to option 4, it has an arrow and then R angle theta. So that's converting from rectangular form into our polar form. Press enter, and I get 17 angle 118.072 and some change degrees, which is the right answer without having to think about whether we're in the correct quadrant. Okay, so that's how you do that conversion for folks with a TI calculator. For a Casio calculator, it is slightly different. Oh, here they are. And it also depends on what version of the Casio calculator you have. For either version of your Casio calculators, the first thing that you need to do is press the mode button and tell your calculator that you want to be operating in complex mode, which I believe is option 2 for both the 115s and the 991s, but let me double check the 991s. Option 2. All right, so for you Casio folks, I would enter this number in as -8 plus 15, and then I press the ENG or the engineering button, and that is how I get my imaginary operator I or J. Now, this is where paths diverge. If you have the 115, in order to do the conversion, you would hit Shift 2. That brings up your complex menu. Option 3 converts from rectangular into polar coordinates. For those of you that have the Casio 991, -8 plus 15 engineering, for you guys, you just press the option button, the one at the top left, and that will bring up your complex menu. Cycle down to the next page, and that is your conversion into polar and rectangular coordinates. All right. So I went through that quickly. Who needs help finding the right buttons? Okay, nobody wants that? That's fine by me. All right, so the overwhelming majority of the mathematical operations and stuff that I'm about to describe to you, and I say the overwhelming majority, literally all of them, it can actually be just done on your calculator. But there are going to be times when I'm going to reference some of these operations in derivations of things and do them by hand. So I just want to walk you through what some of that math looks like in a generic sense. Okay. So the first, that is correct. I do not dabble in the black magic of HP calculators whatsoever. So Google it or YouTube it. I'm sorry. It is. The HP 33S is FE approved. It is the only FE approved calculator I do not own because the order of operations for HP calculators confuses the hell out of me and I'm too lazy to learn it. Yeah. Yep. Don't like it. Don't want to learn how to use it. There's not enough space in my brain for it. Sorry for the 3 people I've ever known that have used an HP calculator. Yeah. All right. So the first operation that I want to talk about is the conjugate operation. I wish this would work better. All right, so I'm going to write here complex conjugate. Okay. And this operation looks like we have a complex number, and then I put an asterisk out by it. This is representing the conjugate operation. Okay. So let me graphically describe what the conjugate operation entails. And then once we know that, we can figure out what's going to happen here. So this is my real axis. This is my imaginary axis. I have my generic complex number A out here. That is A units out in the real direction, B units out in the imaginary direction, and has some phase angle theta A like so. The conjugate operation is simply flipping this complex number over the horizontal axis, meaning that A conjugate would be this guy right here. So we are still A units out in the real direction, but now we are negative B units out in the imaginary direction. What do you think is going to happen for our polar representation? The magnitude is going to stay the same. Our angle is going to change signs. That is all the conjugate operation entails. Change the sign on the imaginary part, or change the sign on the imaginary part for a rectangular representation, change the sign on the angle for exponential and polar form representations. If remembering that is just beyond your capability, your calculator can do it for you. The conjugate operation on the TIs is found in that complex menu by pressing Shift Pi. For the Casio 115s, it's found by pressing Shift 2. For the Casio 991s, press the Option button, cycle down until it says conjugate. Okay. So you don't have to remember how to do it. The calculator can do it for you, but that particular operation isn't particularly difficult. All right. While we are on the concept of a conjugate operation, because we're going to wind up doing this here in a moment, what happens if I multiply a complex number by its complex conjugate? So in polar form, that's going to be the magnitude of A with an angle. Actually, let's do it in exponential form so it'll be easier to see. E to the J theta A this is going to be multiplied by the magnitude of A e to the minus j theta A. What happens when I multiply those two exponentials together? Cancel each other out, so I'll have e to the 0, which is just 1. So any complex number multiplied by its complex conjugate is simply the magnitude of that complex number squared. That's something that we will utilize a couple of times throughout the duration of this class and in other electrical engineering classes as well. All right. Now let's talk about addition. So let's say that I have complex number A is equal to lowercase a plus JB. Complex number B is equal to lowercase c plus JD. If I want to do the mathematical operation of A plus B, that is literally just A plus JB plus C plus JD. And I'm just adding these together as if they were vectors. So the real parts are going to add together and the imaginary parts are going to add together. So I would have a real part of A plus C plus J times B plus D. Subtraction is just addition, but one of the things has been multiplied by -1. So if I had A is equal to A plus JB and B is equal to C plus JD, A minus B is equal to A plus JB minus C plus JD. So that's going to look like A minus C plus J B minus D. There is not any remotely easy way to do addition or subtraction using complex numbers in exponential form or polar form. That being said, your calculator can do it all day long. Just by hand, you want to do it in rectangular form. All right, now let's talk about multiplication. So once again, complex number A plus JB. Complex number B is C plus JD. A multiplied by B will be equal to something. All right. So before I even do that, I want to point something out here. If I'm asking you to multiply two complex numbers together, I'm going to put the two numbers next to each other. End of story. Okay. I am not going to put a cross in the middle to indicate multiplication because I do not want to get that potentially confused with the cross product vector operation because that does not exist for complex numbers. I'm not going to put a dot in the middle to imply multiplication because I do not want to get that confused with the dot product, which does not exist for complex numbers. I'm not going to put an asterisk in the middle because that is what's used for the conjugate operation. So there's literally nothing I can do that is conventionally used to imply a multiplication other than literally just putting the two things next to each other. So just to reiterate, if I'm asking you to multiply complex numbers, it will literally be complex number A next to complex number B. End of story. Sure. I could do, well, yeah, I mean, I could put parentheses around them and all that kind of stuff as well. and explicitly multiply there, that would be okay. And you'll see that in some of the homework assignments and all that kind of stuff. But for a simple multiplication like this, where it's just two things multiplied by each other, parentheses, I think would just be even more confusing. So now that I'm going to expand it out though, I'm exactly going to do A plus JB in parentheses times C plus JD in parentheses. Okay. And I am going to simply FOIL this thing out like you guys learned to do in your high school algebra classes. So that's going to look like AC plus J AD plus J BC plus J squared BD. What is J squared? -1. So that means this thing is going to have a real part of AC minus BD plus J AD plus BC. So when I multiply using rectangular form complex numbers, I can get a rectangular complex number in the output. Now, let's look at multiplication using exponential form complex numbers, right? So if I have A is equal to the magnitude of A, e to the j theta A, and B is equal to the magnitude of A, e to the j theta B, this multiplication looks like the magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B, is just the magnitude of A times the magnitude of B, e to the j theta A plus theta B. So the magnitudes multiply together, add the phase angles, Hojun. Thank you, yes. Should not be the same magnitude. Thank you for that. So multiplication by hand is a little bit easier to do in polar form than it is by rectangular form, but it absolutely can be done. I got 6 minutes to get through division, so I think we're going to be okay. All right, so for division, I have A is equal to A plus JB, and B is equal to C plus JD, then A divided by B is going to look like A plus JB divided by C plus JD. So while this is correct, I don't like this. So let me explain why. Every other mathematical operation that we have done on rectangular form complex numbers has resulted in a rectangular form complex number. This is a ratio of rectangular form complex numbers, but it is not a rectangular form complex number in and of itself. So in order for me to do division using rectangular form complex numbers, I'm actually going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. So that means I'm going to multiply this whole thing by C minus JD over C minus JD. And what we will find now is that we are going to have AC minus JAD plus JBC minus J squared BD divided by C squared minus JCD plus JCD minus J squared D squared. should be very obvious to see that these guys cancel each other out. Negative j squared is simply positive 1. And so from this, we get AC plus BD divided by C squared plus D squared plus J BC minus AD over C squared plus D squared. And now we have it explicitly as a rectangular form complex number like we would expect. So, in short, division of rectangular numbers is a pain in the ass. In polar form, it's significantly easier. So, sorry, A is equal to the magnitude of A, e to the j theta A. B is equal to the magnitude of B, e to the j theta B. A divided by B is just A magnitude e to the j theta A over B magnitude e to the j theta B, which is the same as the magnitude of A divided by the magnitude of B, e to the j theta A minus theta B. I got done with a whole minute to spare. I'll be done. All right. So, you guys have literally a minute to work on the in-class assignment. So let me give you a brief talk about this in-class assignment just very quickly. The goal of the in-class assignment was to get you familiar with using your calculator. That's literally all I want you to do. Do not do any of it by hand. Okay. So I will be more than happy to entertain questions about how to properly use your calculator and all that kind of good stuff. In fact, I will go down the hall into the project-based learning area, kind of waiting room, if any of you guys have any questions about how to use your calculator, and I'll hang out there for the next little bit